Hello everyone, today we're going to be talking about my topic on quantum physics, which is wave-particle duality. What is wave-particle duality? Wave-particle duality is one of the key foundations in quantum mechanics. Essentially, it's a mathematical way to describe how particles behave at the atomic scale. At the atomic scale, everything is the size of an atom. It's a level where details of atom-sized particles are the main focus. For example, water, which is made up of 2 hydrogen atoms and 1 oxygen atom. It also shows how particles behave at the subatomic scale. Now, the subatomic scale is below the atomic scale. Here, things are even smaller than atoms. Instead, they include things that make up atoms, for example, protons, electrons, and neutrons. Some of you may have heard the saying that light can act like a particle and a wave by bouncing off a mirror like a particle and bending like a wave. So just like light, particles can also act like waves. That's demonstrated through something called wave functions. A wave function can be presented as the mathematical formula used in quantum mechanics. This formula tells us everything we need to know about a tiny particle such as an electron or photon. The wave function gives us an idea of where the particle might be, its actions, and what it's likely going to do. However, wave functions do not tell us the specific location of the particle. Now that we know what wave-particle duality is, let's discuss the major topics tied to it. The first one is quantum mechanics in terms of wave-particle duality. Quantum mechanics is the branch of physics that helps us understand how small things such as atoms and particles behave. Particles are not viewed as tiny balls, but instead they're seen as waves. We can use wave functions to show where the particle may be, as well as measure their location at a specific time. In order to understand wave functions in terms of quantum mechanics, there's 3 rules we must know. The first rule is that particles act as waves when they aren't being observed. This means that particles are not at a specific location and appear unclear before they are measured. Right after they're observed, they become fixated on one location. Essentially, they pause for a moment in time and stay at this one location. The second rule is that when particles are observed, they act like particles. What this means is that the particles do not act like waves. It doesn't interfere, spread out, or have one specific location. The third rule is that the 2 behaviors are both real. It all depends on how we view a specific side at a certain time. So basically, when particles are not being watched, they will act as waves. But when they are being watched, they're gonna act like particles. To understand this better, let's look at the second major topic, the double slit experiment. In the early 19th century, a significant discovery was made by Thomas Young through an experiment. His discovery was one of the biggest developments of modern physics, as it showed that particles, including electrons, have both wave-like and particle-like behaviors. At first, the experiment was done using light. A beam of light was directed at a barrier with 2 slits or holes, a screen behind the barrier where the light shines through when it passes the slits. This creates a bend, or also known as an interference pattern, behind the barrier. An interference pattern is when a bunch of waves come together and combine. When this happened during the light experiment, the light had the same characteristics as a wave. The light showed diffraction. Later on, a huge shift in the experiment occurred when it was repeated, but this time it used electrons instead of light. Let's visualize this. If we were to throw a bunch of electrons from an electron beam through 2 slits, not only 2 spots will be affected, instead a pattern will occur behind the slits. We can even do this by throwing only single particles through the slits. The same thing will happen. They'll go through the slits and build up and combine over time. This combination of particles creates the interference pattern, which is also called a wave. The last main topic I have today is the de Broglie wavelength. In 1924, Louis de Broglie introduced us to the concept of the de Broglie wavelength. His work told us that not only do waves carry particle-like behavior, but particles like electrons also have wave-like properties tied to them. He came up with his theory by building up on Max Planck and Albert Einstein's theory on light. He came up with a conclusion that stated that all moving particles exhibit wave-like properties. This was determined by Planck's constant divided by the particle's momentum. This equation shows us the relationship between the wavelength and momentum of the particle. For example, if we increase the momentum, then the wavelength will decrease, and vice versa. Just like the de Broglie wavelength, the Schrödinger equation is linked to wave-particle duality. This all is also linked to the Heisenberg uncertainty principle, meaning we can't know both a particle's position and momentum all at once. The more we measure one thing, such as position, the less we know about the other, like speed. So overall, wave-particle duality tells us that particles can act as both particles and waves. Equations and experiments not only prove how particles behave, but also help us predict a particle's behavior. That's all. Thank you so much for listening.